So now you take your solar cell and you make it into a module or a panel, and the current that you get out of it depends on its area. So a modern solar cell will produce half a volt at 8 or 9 amps, which is a lot of current. So what you do is you put them into a panel, you wire them all in series, and when you wire in series, you increase the voltage. Now you can take those panels and you can wire those in series to get a higher voltage. For a grid connected system, what it'll be made of: solar panels, an inverter, and some switches. Well, the inverter's job is to convert from DC to AC. That's all it does. And where does the output of the inverter go? It goes to a circuit breaker in your circuit box. And now, when you're generating solar electricity, that electricity is going to feed your loads first, because that is the path of least resistance. If you don't have things turned on or you don't have enough load, the excess goes back to the grid. That kind of system involves a string inverter where you're wiring your panels in series to get to a higher voltage first and then going through your inverter. In the last 10 years, we've seen the rise of the microinverter, and the microinverter takes the 40 volts out of one panel and converts it to 240 volts AC. So now you can have a system with a little inverter and small on each panel. They're wired in parallel, and the output of them again goes to a breaker in your circuit box. It's a little faster to install that, and if you have different orientations of your panels and things, it'll make the system a little more efficient than a string inverter. So that's a grid tie, and then there's off-grid or standalone. Standalone involves your solar array, a charge controller, a battery bank, and an inverter. That is going to involve batteries. Net metering, so we've talked about net metering, and that is for grid ties. Obviously you don't need that with off-grids, but with grid ties you need net metering or something like it. Good morning. It's time for a little show and tell. We're going to look at some solar hardware. Start off with the prime mover, the photovoltaic module. I have one behind me here, and I wanted to give you an idea of how big it is. It's about 65 inches tall and 40 inches wide, so it's a good sized thing. This is a 305 watt module. We now have 320 watt and 330 watt modules that are the same physical size because they keep improving the efficiency of the solar cell. Now we'll take a look at the back of it to see what the wires look like. Okay, so now we're going to take a look at the back of the photovoltaic module where the electricity comes out. So we have a little box back here, which is really just a place to protect where the wires go into the module in the back of it. And we got a positive and negative DC wiring coming out of here with some connectors that are interlocking so that you can wire this to either another module or a microinverter. The cabling on here is photovoltaic wire, and that is similar to USE2 wire in that it's sunlight resistant and it has a nice thick jacket on it. In fact, PV wire has a little bit thicker jacket than regular USE2 for more protection because it's going to be out in the elements. Nevertheless, here's a piece of PV wire that some squirrels chewed. So it's good to have that extra thickness, but even that extra thickness doesn't always protect against squirrels. The interlocking connectors on the ends are watertight, so they can survive out there in the elements for a long, long time, keeping water out of them. So just a couple of details now on what goes into the system. So I said there's the solar panels, there's the inverters, but there are also other components that you have to think about. So you have to think about your disconnect switches and your wires that have certain things you have to do to size those properly. You have to make sure your system's grounded. I said that most of these systems you plug into a breaker in your circuit box, but there are other ways of doing it. There are some rules about how large a system you can plug into your circuit box. So if you need a system bigger than that, then we put it in a little differently. There might be a production meter involved in that, so you can see how many kilowatt hours you're producing. And we also now install a data logger, which means you can monitor what the system is doing. It uploads it to the internet, and you can go look on your computer to see what your production has been. If there's a problem, we can look at it and see, well, do we think it's a problem, or is it just that there's snow all over your panels and they're not producing? And one thing to know that is sort of a point of confusion, so the utility, they come along and they put on a bidirectional meter, if there's not one already. And nowadays, the bidirectional meter that can go both ways is a digital meter. It has some little arrows that point one way when you're exporting and the other way when you're importing. It only tells what you imported and what you exported. It does not tell you what you generated and used. So you can only find that out if you have a consumption monitoring kit on your system. Most of the inverters show that as well, either on their little display or if it's a microinverter on the data logger. You can see what your total production was. If you have a consumption monitoring kit, then you can figure out, well, what did I generate and use sort of separately from what got exported to the utility. So system components, we got the modules or panels, the inverter. So the racks, people will put these on their roof or on the ground. The racks and rails and things that the panels are clamped to, those are made of mostly aluminum. The balance of systems, that's all the other stuff. You know, all the disconnects and overcurrent devices, aka breakers and fuses. The solar module or panel, most of them come in one of two varieties. They are either made of single crystal silicon solar cells, which are the most efficient ones, or they're made of polycrystalline or multicrystalline solar cells, which are almost as efficient, but they're cheaper. To make a single crystal of silicon is a pretty high art, and you typically get a cylindrical shaped crystal. And now you got to slice that up, you got to make it fit in a square panel, so you have to cut off some corners. That's why you see the little white diamonds on the solar module. That's a good indicator of that it's single crystal. And all that is pretty tricky and more expensive than the other way. A polycrystalline, you melt your silicon, you pour it into a mold, which could be rectangular or a square mold. It's not as tricky to make, so it's a little less expensive. Both those kinds are very popular. Probably the biggest type of other kind of material for a solar cell is cadmium telluride. That's probably less than 1% of all the solar panels and modules that are made. So what are these things like? So this is a 320 watt panel from Trina, 320 watts. So what's in this spec? So this is just the DC side of this. First of all, the numbers on here are given at a specific test condition, which is called the standard test condition, or STC, which is when the cell temperature is 25 degrees C and the irradiance is 1,000 watts per square meter. There's a voltage when there's no load. So it's not hooked up to anything and you put your meter on it. That would be the open circuit voltage, or VOC. Then there's the voltage when it's powering something. So it's hooked up, it's going to the inverter, the voltage is dragged down when that happens. And notice how they call that the maximum power voltage. Nothing on this sheet is truly the maximum, because the voltage changes with temperature and the current changes with light. So 25 degrees C, that's what? That's 73 or 4 degrees Fahrenheit. It's wintertime. It's a lot colder than that. And because it's a lot colder, the voltage is higher because it's a semiconductor device. When the temperature goes down, the electrical resistance goes down, and therefore the voltage goes up. There's a short circuit current, meaning if you just hook the panel to itself, which by the way you can do, that's a short circuit current. It's kind of the most current it produces because it's not serving a load. And then there's the operating current when there is a load, which is a little less. But again, none of those numbers are maximums, because if there's more than 1,000 watts per square meter of light, then you're going to have more current, because the current out of a solar cell is linear with light. They also show the efficiency on here for converting light to electricity. There's efficiencies of cells. Okay, so the solar cell itself, they took it to NREL, they had to measure the efficiency, and it's going to be higher for the cell than it is for the panel, because once you wire a whole bunch of them together in a panel, the efficiency is less, simply because there's a little bit of voltage mismatch between cells. So these are a couple of different kinds of inverters. A microinverter goes on each module. Some modules come with it already built in. So I don't have to do any DC wiring with a microinverter. I can just plug them together in parallel and then go right to my breaker. But all inverters have some other properties that are really important for use with the grid. They produce a true sine wave AC. The inverter can synchronize perfectly with the utility's grid. Its voltage and frequency can match what the utility's doing. So it has to do that to be tied to the grid. It can also detect problems and shut itself off. So if the grid voltage or frequency is out of range, there's some specs the utility has, like there's some problem with the wires out there, then the inverter will shut off. And if someone fires up their generator due to power outage and they accidentally backfeed the grid, the inverter could tell the difference between that and the real grid and stay off. You can also get inverters that will produce 208 volt three-phase power. You can get inverters that will produce 480 volt. Now those are more for the commercial side. A lot of commercial buildings have three-phase 208 or 480. So you can actually get inverters that do that. If you're doing utility scale stuff, then generally what ends up happening is you have a transformer somewhere to step the voltage up to whatever the main grid needs, which could be 15,000 volts. All right, so microinverters and string inverters. If you are putting up a system that has all your panels in a single orientation and there's no shade, string inverter works great. If you have some different roof orientations, you could use microinverters. What microinverters will do for you is essentially make every panel is working sort of independently. Whereas with a string inverter, think about when things are wired in series, if something happens to that series string, like you shade one panel, it tends to shut down the current for the whole thing. So that's why the string inverters work best if you've got the same orientation and no shade. So the panels or modules and the inverters, that's the core of your system. Next up, we have a couple of microinverters. This is a microinverter that serves one module. So it has plugs here where the output from the module gets plugged into the inverter. And then there is another cable that plugs in here to send AC 240 volts out to your circuit box, or you can wire in parallel to the next module. Typically, there will be a dozen of these wired in parallel that goes back to your circuit box. So that's the nice thing about these microinverters is that each module works independently. If one is shaded, it doesn't affect the other ones. It also serves the need for rapid shutdown in that once the AC is lost, if someone pulls the meter or flips the switch downstairs, then there is no voltage coming down from the roof. This one can handle one module. There's another kind that can handle two modules. So that's and then this one has a hardwired in AC cable to go to the next inverter. So same idea, but you can actually serve two modules with this one. This one I kind of also like. It has these nice grounding things on here to dig into the rail frames, so it makes a good ground connection. A string inverter, we'll see if we can find one of those, but that would be wired by wiring these cables together in series. So you might have a series string of 10 or 12 modules, so you're basically plugging these wires one to the next to get a series string, and you'll end up with about 450 volts DC going to a string inverter. These kind of microinverters you can attach to the rails behind each module, and they have ground clips and things that go on there. There are also some modules, so-called AC modules, that have these micros built right into the module, so it's already attached to the module. That's we really like that because it's quicker to install, less attaching of things. But the ones that are not attached to modules obviously can work with many different kinds of modules too. So pluses and minuses of that.